Hello everyone, welcome to this last video on max and min problems. In this final video, we will make use of our knowledge of functions and calculus to solve maximization and minimization problems. The first situation we'll discuss are max and min situations on a closed interval. If a function f of x is continuous on a closed interval a to b, then it will attain an absolute maximum and an absolute minimum. This is called the extreme value theorem. Points where these can occur, the max and mins that is, are limited to actually a few candidates. It must happen either at the bounds of the interval or at critical points within the bounds. Critical points could be either stationary points or points where f prime is undefined. So here are guidelines you can follow to solve problems that involve maximization, minimization on a closed interval. Firstly, identify the bounds of the function. In some circumstances, they'll be given. In others, you have to rely on the context of the problem to find these bounds. Identify all critical, stationary or not, numbers that are located within the bounds. So this will involve differentiating, finding all values of x that generate a derivative that is either 0 or undefined. Evaluate the function at all the x values you have listed above. Since the number of candidates is restricted to bounds and stationary points, really at this stage we're just comparing which one will produce the highest value or the lowest value. And then conclude. For example, let's find the min and max values of the function x cubed minus 3x over the interval 0 to 3. Following the guidelines, first step is to identify the bounds, which in this case are explicitly given. Secondly is to find critical points of the function. So we are differentiating x cubed minus 3x, which results in 3x squared minus 3. We can then factor into 3 times x minus 1, x plus 1. So basically, stationary points within our interval are limited to just x equals 1. Even though x equals minus 1 is a stationary point, it falls outside of the interval that we were restricted to. And now we have our list. The function can reach a max or a min either at the bounds, so here is the function's value at the left bound 0, and at the right bound 3, or max and mins could occur also at critical points between the bounds, which occurred at x equals 1. The function's values at bounds and critical points are then compared, and we can conclude that the maximum value of f occurs at 3 and its value is 18. The minimum value of the function occurs at 1 and is equal to minus 2. Max and min can also be examined on an open interval. If a function is continuous on an open interval, then finding its min and max values will entail going through the same procedure that you would use to curve the sketch, to the exception of finding the concavity of the function. Because this resembles the curve sketching section of the course, we'll actually not do an example, but here is a reminder of the steps that you would want to follow. So guidelines are, first of all, identify any bound that must be imposed. Although we are talking about open intervals, occasionally we will be limited perhaps on one side or on the other. We'll identify all critical points, all critical numbers that are located within the bounds. And we're going to use a table of variations to detect max and min. You can actually do a quick curve sketch of the function in order to visualize where the max and mins could occur, perhaps compare 2 or 3 different local mins, local maxes. If you absolutely need to identify absolute max and min, then you can also include the horizontal asymptotes in order to figure out if the function's asymptotes will allow you to conclude 2 absolute mins and maxes. The most complex situation, and the one that we will pay most attention to, are max-min situations with a constraint. Occasionally, situations will require that multivariable problems be maximized or minimized while respecting a set of constraints. One of the main goals when approaching these problems will be to reduce them to one-variable situations. So here are max-min situations and guidelines we can follow when constraints are imposed. So firstly, you're going to have to identify and possibly model the objective function and the constraint. Starting from the constraint, isolate a variable that is, express it in terms of the other variable or variables. Substitute the isolated variable in the objective function using the result of the previous step. And finally, we will find max and min of the function based on steps that we described a little bit earlier on open or on closed intervals. Here's an example that will require that we model both the objective function and the constraint, and then lead on to finding the maximum value. So here is a NASCAR oval, so it's an elliptical racetrack, and is described by the equation of an ellipse, 4x squared plus y squared equals 4. Inside the track, which is shaded in the picture, a rectangular area is delimited to allow fans to park their recreational vehicles. What are the dimensions of the rectangle that will maximize the parking area? So basically, we need to figure out at what coordinate point xy one of the corners has to be placed so that the rectangle that is generated has the biggest possible area. If we can find the coordinate point xy in the first quadrant, then by symmetry all of the other corners will follow. So we're going to restrict ourselves to that first quadrant. So max and min with a constraint. So first we said we needed to identify the objective function and the constraint. So our objective is actually to maximize the area of the rectangle. The length, or maybe I should say the height of the rectangle, is x in the upper half and minus x in the lower half. Again, this is symmetry. So x is the distance from the horizontal axis to the corner, and the same distance would apply to the bottom half. So 2x is the height, 2y is the width. So 4xy is the area of this rectangle. As for the constraint, we said that x and y are the coordinates of the points that must lie on the ellipse. And we're also going to focus on only coordinates that are in the first quadrant. So whatever x and y are, they must respect the constraint 4x squared plus y squared equals 4. And we're going to add on to that x and y be positive, again, because we're focusing on the first quadrant of the ellipse. So our objective is to maximize the area, 4 times x times y. The constraint is to satisfy 4x squared plus y squared equals 4, regardless of the x's and y's we pick. The second step of our guideline was to use the constraint to isolate a variable. So from 4x squared plus y squared equals 4, perhaps the easier choice is to isolate y squared at first by subtracting 4x squared to the right. 4 is common and can be factored. And we can find the corresponding value of y by rooting both sides. Now, again, in this case, there should be 2 possible values of y. But since we are restricting ourselves to the first quadrant, we're going to retain only the positive root, 2 times 1 minus x squared rooted. Our next step said substitute the isolated variable into the objective function using what we had done in the previous step. So our maximization has to be applied to the objective function a equals 4xy, and we have just found that y must equal 2 root of 1 minus x squared. So we are replacing, this is why we call it a substitution method. We are substituting y by its relationship it has to x. So 8x times root of 1 minus x squared. So there's been quite a few steps of algebra, but at this stage, notice how the objective function no longer depends on 2 variables, but rather just 1. So we have now returned to a 1-variable max and min problem, and this would be considered to be on an open interval since x can be greater than 0, and there is no telling how big x can be. Someone could also say x is a closed interval problem because according to our picture, x has to stay on the ellipse and therefore has to stay between 0 and 1 if you go back to the picture. So one or the other would be fine. So now we're going to find the max and min values of the area based on the 1-variable function that we just constructed. Here we go. Here is the area of our, as described in terms of x. Now to find max and min, we need to identify critical points. So as a first step, we need to differentiate function a in terms of x. There's definitely a product rule to apply here since 8x is multiplying with root of 1 minus x squared. So derivative of 8x is 8, and the derivative of 1 minus x squared requires a chain rule. So that explains that second term, which I'll leave to you to verify. Combining everything with one single common denominator, we can then simplify the root at the numerator, combine powers of x, and a reduced form for a prime will be 8 times 1 minus 2x squared over the root of 1 minus x squared. We will find that a prime is equal to 0 if x is equal to 1 over root of 2. Obviously, x equals minus root of 2, 1 over root of 2 is also a possible 0, but it is not in the first quadrant, so we would restrict ourselves to this one possibility. A prime becomes undefined when x is 1. That would be the extreme edge of the ellipse, but then it would have no height. So I've disconcerted, I've discarded it, and we'll see in our table of variations later that it makes no difference to the result that we were actually looking to obtain. So for now, we're just going to focus on the critical number x equals 1 over root 2. Knowing that x is 1 over root 2, we can backtrack and figure out what the corresponding values of y, in this case root of 2, would be, and of the corresponding area, which we get by multiplying 4 times x times y. There is one last detail, though, we have to check. There is no guarantee that the value of x, 1 over root 2, is indeed a max. All that we've shown is that it is a stationary point. So we will do one last verification, which involves a number line. Just like usual, as if we were graphing, we have highlighted the fact that 1 over root of 2 is an x value that creates a stationary point. And I've used test values left and right of this stationary point to identify the signs of the area, the signs of the derivative of the area. As we can see from the table of variations, we can now confirm that an absolute max occurs when x is 1 over root of 2.